Hello guys, it is Mr. C, and today we are going to cover some vocabulary. We're going to basically be putting together a small dictionary of geometry basic terms that we're going to be using for the rest of the school year. Okay. The first few terms we've already seen this school year, we've already gone over, but we're still going to recap on them so that you have this to reference. Okay. So the first thing we're looking at is a point. Remember, a point is a location with no size or shape. All right. It is considered a location, but it really has no size or definitive shape. So with no size or shape. And whenever we see points, whenever I'm looking on a plane, looking on an object or a figure, points are always given to us as a dot. Remember, they're given as a dot and they're labeled with a capital letter. So this is point A, this is point B, and then we have point C. So these are three points given on a plane. All right. The next thing that we are going to look at is a line. A line is made up with points with no thickness or width. A line is made up of points with no thickness or width. So we will have some amount of points. You always have to have at least 2 points. So let's say this is point X and this is point Y. And then a line passes straight through those 2 points. Because remember, lines always operate in a straight manner, onwards and onwards forever. I'm going to cheat here. I'm going to use the line tool. But I imagine that some of you are true artistes and will be able to draw the line with no issue. But there is my straight line. And when we name those, don't forget, because it is a line going both directions forever, we use 2 arrows to show that. And we name it based on those 2 points, capital X, capital Y. So this is line XY. All right. Now, going a little further from points and lines, we have line segments. A line segment is a measurable part of a line, okay? So, remember, a line extends on and on forever, but a line segment is just like a clip of that. It is a measurable part of the line. Measurable part of a line. Consisting of 2 end points. Okay, so we can't have a line segment without at least 2 end points. So think of the line that we just had, but it's not extending on and on forever. It is just a segment of that line. It is a piece of that line. So if I call this point R and I call this point S, think of it as that specific part of the line. I won't use the line tool there. I won't cheat. That is the line segment RS. And the way I would name these, well, first of all, line segment RS is a good name. But visually, what I would see is we have that line, no arrows, because we're not going in either direction forever. We're just looking at a piece of the line. And then capital R, capital S, could do it SR as well, as long as the endpoints are represented. Okay, so that is a line segment. And then we have array. Array is a line that extends indefinitely. So that means forever. It extends forever in one direction. So a line that extends indefinitely in one direction. Indefinitely. In one direction. You could also say infinitely. Both of those are synonyms. They have the same meaning. In one direction. In this regard, they're synonyms. So array, we will always have an endpoint. The endpoint is crucial for us. And then it will extend through another point, at least one more point, and then on forever in one direction, because it is a line that goes on and on forever in one direction. All right. So let's say that this end point here is E, and then the other point that we have here on the line is F. Rays are always going to be a single arrow to the right. Okay, ray, right, starts with an R, single arrow to the right. And then I am going to label them by the end point first. So F would never come first in this situation. The E will always come first. E, F. Okay, endpoint or ray, E, F. All right. Now, let's go ahead. We got to keep moving. We got quite a bit to cover here today. And from array, we're going to start thinking about planes. Remember, planes are one of our undefined terms. Planes are a flat surface made up of points that extend indefinitely in all directions. So once again, we are extending indefinitely, but now we're going in all directions. That extend indefinitely in all directions. You can also use the word infinitely, indefinitely, in all directions. All right. Picture-wise, we usually just represent this with like a rectangle, some sort of parallelogram. This is my plane. It's my flat surface. Almost think of planes as like a piece of paper, but it doesn't end at the edge. There is no edge. It just goes on and on forever. So sorry. There's my rectangle. And it is made up of points. So I'm going to go ahead and put some points on there. We'll call this K, call this one L, and we'll call this one J. Now you'll notice I have to have 3 points. At least 3 points make a plane. And then I will name this plane P. Capital cursive letter. Or I could also just name it by these 3 letters. Plane JKL, LKJ, LJK. All right. But these are the ways we identify it. There are 3 points that help us make this plane. And then we identify it by its cursive letter that is not connected to a point. Be aware that sometimes we will have the cursive letter on the plane, but it's not connected to a point, so it is actually just the name of the plane. Now, you'll remember when we talked about planes and we talked about lines and points, we said that sometimes things are collinear. Collinear are points that lie on the same line, okay? Some of this we have discussed. You have this definition. Points that lie on the same line. Okay. Now, when we say collinear, and we're talking about points that lie on the same line, what that looks like is quite literally, I have a line, and then on that line, any point that is on that line is collinear. So if this is L, this is M, and this is N, then I can say that L, M, N are collinear, okay? It's important to note that if I tell you they're non-collinear, they do not lie on the same line, okay? And so I'll just make like a little probably should have given myself a little bit more room, but non-collinear do not lie on the same line. Points do not lie on the same line. I'm running out of space here, but we'll just put it right here. It'll be fine. All right. So if it's collinear, that means it is a point that is on the same line. Remember, co is like together, they share, and then linear is a line. So naturally, coplanar, that means they share a plane, okay? So if it is coplanar, it is points that lie on the same plane. And as like an addition to that, they lie on the same plane. As an addition, we also talk about non-coplanar, okay? These are those points that are not on the same plane. So I will go ahead and write this before I draw our little picture. So non is kind of the big go-to there. Non tells us they don't. So non-coplanar do not lie on the same plane. And that's why I'm writing it in blue. It is different. These are two different things. Coplanar are on the same plane. Non-coplanar do not lie on the same plane. Okay. And my example here, if I have a plane, remember a plane is basically, we illustrate it kind of like a rectangle. I have, this is going to be plane QRP, or PRQ, however you want to name it. Call that R, and we'll call this P. And we have, I don't know, we will name this plane B. Okay, remember we always have a recursive letter to name that. So I can say that P, Q, and R are coplanar. They are sharing that plane together. They make that plane, because remember we need at least 3 points to create a plane. So being coplanar is also just part of existing on the plane, right? Now, we're going to move on away from planes for a second. We're going to talk about congruent segments. Now, congruent segments occur if two segments have the same length, all right? Remember, to be congruent means that it's the same size, same shape, same angle, okay? Sometimes we don't have angles. Sometimes we don't necessarily have a shape, but then we look at the size, right? So congruent segments occur if two segments, it's in the name, segments, right, have the same length. Then they are congruent. That makes them congruent. So let's say I have line segment, what's this? We'll call this AB. This is line segment AB. I did my best. That's all we can ask for. And then I have line segment CD. These are not drawn to scale, so if you measure them, they might not be exactly congruent. But the idea here is if, let's say, this one was, I don't know, 8 inches, and this one was also 8 inches, and I'm just going to 8 inches, sorry, space kind of tricked me there, then these are congruent to each other. They have the same length, right? And because they have the same length, there's a few ways we can think of this. I can say that the distance from A to B, and that's why I write it like that without a line, because I'm just pointing out the distance from A to B, is equal to the distance from C to D. And because of that, we can write a congruent statement. Because we know they're equal to each other, we can write the congruent statement that says line segment AB is congruent to, and remember you have that little swirl above the equal sign to make the congruent, line segment CD, all right? So congruent segments are segments that are congruent to each other. They're of the same length. Which brings us to the first postulate that we really discussed, which was the segment addition postulate. The segment addition postulate states that if A, B, and C are collinear points, okay? So if A, B, and C are collinear points, and B is between A and C. So imagine that A, B, and C are all on the same line, and B is somewhere in between A, B, and C. And B is between A and C. Then, this is where the postulate comes into play, then the distance from A to B, okay, or we can just treat it as a line segment, plus the distance from B to C, or we can just treat it as a line segment, is equal to the distance from A to C. Okay. And to make that make sense visually, if I have a line with 3 collinear points, they're all sharing the same line. So we have A, we have B, we have C. Okay. And then we have a line that passes through all three of them, going on and on forever. A, B, and C. And B is in between them. You'll notice I didn't put B in the center. It's not guaranteed that B is in the center. The only guarantee is that B is somewhere in between them, A and C. Okay? Then that tells us that the distance from A to B plus the distance from B to C will give me the total distance from A to C. So again, writing that A to B plus, I'm going to do this one in blue because I gave you that line in blue, B to C gives us A to C, all right? Gives us the whole line, A to C, or at least that line segment from A to C, all right? So far we have covered most of these things in class, but now we're going to move to a few new things. The first of those things is going to be what I call the distance formula. We will work with this in the coming weeks. We will have to solve equations using this. So we want to make sure that we have this so we can reference it when we need it. Okay. This is the formula that we use to find, well, distance. Okay. This is the formula used to find the distance between 2 points on a coordinate plane. The formula used to find the distance between 2 points on a coordinate plane. I know this is quite a bit of writing, but as you can see, we are in this together. All right, coordinate plane. So we are on a plane made up of points. Those are coordinates, right? Those are locations. And we're trying to find the distance between two of those points. Okay. And the way we think about coordinates or points on a plane is in terms of x and y. Remember our x and y axis? So our formula is the distance is equal to, okay, the square root of, that's right, the square root. And you'll notice this is a big radical we're making here. And in parentheses, x2 minus x1. So we have two different x coordinates because we're talking about the distance between 2 points, right? Squared plus the distance between y2 and y1. So we are subtracting those as well, okay? And they're also squared. So we are looking for the distance between the x's, that's why we're subtracting, the distance between the y's, and we are finding the overall distance based on that, all right? That is the distance formula. We will see it put to use in the coming weeks, but we just want it for reference right now. Midpoint formula, okay? This is the formula that we are going to use when we need to find the midpoint. The formula, and I mean it's in the name, formula used to find the midpoint between two endpoints. To find the midpoint between two endpoints. So earlier when I drew my A to B, B to C, I did not put it in the center. Maybe I don't know where the center is, but midpoint formula tells us where the center is. The midpoint between two endpoints. Okay. And we are still thinking in terms of x and y. We're still thinking in terms of where they are on a coordinate plane. So midpoint, capital M here. And this is all in parentheses because this is a coordinate that we are finding. We are finding a specific x and a specific y. Okay. And it is the distance. It is x1 and x2 together. Okay. And then we are dividing by 2. We're finding the average of these 2 points, right? That's what we're doing. So if I divide something in 2, I'm splitting it down the middle. We're looking for the center, okay? And then, of course, that is my x-coordinate. Now I need to find my y-coordinate. That's why I have this comma here, okay? So comma, and then y1 plus y2. And I am also, we're looking for the average here. We're looking for the average distance, or the median, the middle of those 2 points. That's what we are doing here. Okay, so that is the midpoint formula. Moving on. Segment bisectors. All right. A segment bisector is when we have a segment. Remember, that's just a piece of a line, or a plane. A segment, a line, or a plane. So a few different things can do this, right? That intersect a segment at its midpoint. So one of those things, a segment, a line, or a plane, is intersecting this specific segment that we're going to look at the midpoint. Intersect a segment at its endpoint. Or not endpoint, my apologies, midpoint, at its midpoint. I had said midpoint to begin with. Midpoint. Right? And what this looks like is if I have, we'll say, line segment, or no, that's a line. I don't want a line. Just back up a little. Okay, we'll say that I have line segment A to B. Okay, that's A, B. And then passing right through the middle, and we're going to label the middle with a capital M for midpoint. Passing right through the middle, we have a line, and I'll call this line L. Okay, that line L is passing right through line segment AB. So line L is a segment bisector. Okay, it is intersecting, it is cutting it into 2. Bi meaning 2. So it is cutting it into 2, and more importantly, it is cutting it evenly into 2. So it is perfectly in the center, okay? We are lucky today. Let's see here. We actually don't have to worry about directed horizontal or vertical components. We are going straight into our next stuff. which is how we look at lines and how they work together. So remember I talked about segment bisectors. Well, sometimes we have lines that are perpendicular to each other. So now we're looking at things that intersect each other, okay? Perpendicular lines are two lines that intersect at a 90-degree angle. And this is important. Just because they intersect doesn't make them perpendicular. They have to intersect at a 90-degree angle. At a 90-degree angle. 90-degree angle, okay? And whenever I talk about something being a 90-degree angle, we also think about that as a right angle, which we'll define later on, but I still just want to label that that's right. That is a right. And I'm just going to use angle for space purposes. That is a right angle, okay? That symbol is what we use. Now, for perpendicular lines, whenever I am writing this, because I don't want to write the word perpendicular over and over and over again, not only that, perpendicular doesn't translate the same into every language. So we have a symbol in the math world that we use for it, and the symbol that we use for it looks like this. Okay, a line and another line that is intersecting it. Okay, and they're at 90 degrees. Okay, that is the symbol I use for perpendicular. So I could say that we have line L. Okay, I'll just call that L. And then we have passing through it, not necessarily at the center, it doesn't have to be at the center, but passing through it at a right angle. That's how we label right angles if you weren't aware, is line M. Okay, so this is an example of perpendicular lines. They are intersecting at a 90-degree angle. That is a 90-degree angle, all right? Now, sometimes we have something called a perpendicular bisector. A perpendicular bisector occurs when a line, segment, or ray, one second. Line, segment, or ray perpendicular to a segment we have a line, segment, or ray that are perpendicular to a segment at its midpoint. Okay, perpendicular bisectors occur when we have something that is perpendicular to that at its midpoint. Okay, at its midpoint. So what that looks like is if I have, we'll call this line segment AB, A to B, and then we have a line segment XY. Sorry, that's a little curved. I will redraw that to try to do my best. It's a little bit better, but we'll call that line segment XY. Okay. And XY is perpendicular to it, but more importantly, XY is at the midpoint. And the way we can illustrate that something is at the midpoint is we can say that this side is the same as this side. Remember, we can use tick marks for congruence. So I can use one to illustrate that they're congruent to each other, or they can both have two. The point is that they share the same number of tick marks, so they are congruent to each other. XY is at the midpoint, and this is illustrated by us saying that A to this area right here is congruent to this area to B, okay? Another way, in terms of intersections, is parallel lines. Parallel lines don't intersect, okay? They are two lines that never intersect. Two lines that never intersect. No matter how far I go down the line, I will never meet up with another line that is parallel to it. They will never intersect, okay? Two lines that never intersect. And there is a symbol we use for them too. And the symbol that we use for parallel lines, that way we don't have to write parallel over and over again and forget how many L's go in or don't go in, is just this. They are two lines that are like parallel to each other. So, for example, if I have line L, and I'm saying it's line L, so I'm going to name it line L, and then I have line M, I'm going to call that line M in cursive, then I can say that line L is parallel to line M, okay? This is a way for us to quickly indicate that the two lines are parallel, okay? The next thing that we are moving on to, we're getting away from lines, okay? We're done with lines for just a second. I mean, not really, but we're now looking more at what those lines form. And what we have here is an angle. The angle occurs when we have an intersection of two lines, all right? The way we're going to talk about it here is the intersection of two rays, but two lines form an angle whenever they intersect each other. The intersection of two rays at an endpoint. At an endpoint. If you have two lines that intersect with each other, they form angles on the inside and outside. But if I am looking at a single angle, an angle all by itself, this is formed by two rays. So here is my first ray. Okay. First ray, and we'll call that ray BA. Remember, rays have to start at the endpoint when I name them. And then my second ray, which shares an endpoint, starts at B, passes through C, and then goes on and on forever. We'll call this point C, okay? And the way I name angles is always, this is the sign for angle, and it is going to be A. B is the endpoint that they share, okay? That is my vertex that we're about to talk about. So it will actually exist right here in the center. This is angle ABC. Okay. Our vertex is the common endpoint of an angle. Okay, it's where they intersect at. The common endpoint of an angle. So that endpoint that the two rays shared, that is the vertex, the common endpoint of an angle. Is where they intersect at. So where the sides intersect. All right. Now, if I look, I am going to give us the same angle. Okay. This is angle A, B, C, but more specifically, this spot right here is what we call the vertex. That is the vertex. Okay. Keeping up with angles. Now we're going to talk about specific types of angles. These are things that we have seen. 8th grade geometry. We were introduced to right angles in algebra. Here we are using them now. Okay. Right angles are angles with a degree measure of 90 degrees. An angle with a degree measure of 90 degrees. So if I have a line and another line and they form a 90-degree angle, remember we're going to use this box to denote a 90-degree angle. All right. This is 90 degrees. That box tells me that's a 90-degree angle. Okay. We also have an acute angle. That's an angle that's measures are less than 90. So an angle with a degree measure less than 90. I'm putting less than in all caps. Less than 90. Okay, less than 90 degrees. So an acute angle should be a little smaller than 90. This angle, let's say it's 50 degrees. It's probably actually legitimately smaller than that. But that angle that we see there, that is an acute angle. So if this is angle X, Y, Z, then that angle is 50 degrees, okay, which is acute. It's less than 90. Obtuse angles, well, we've been less than, and we've been the same as, so all we can be now is greater than. All right? It's an angle that is greater, an angle with a measure that is greater than 90. Greater than 90. So what those typically look like is something like this. We have those intersecting rays, but they are wide open, okay? So if I call this JKL, JKL, and we could say that this angle here, okay, is anything greater than 90, 100, 110, 140, okay, greater than 90. Not anything greater than 90, but the angle that we are currently measuring is greater than 90. Okay. Then we have something called a straight angle. That's right, we can have angles that are straight. They are still two endpoints that are coming together. They're sharing that endpoint. Okay, there are two rays that are sharing that endpoint. And so, since they are straight and they are sharing the endpoint, they've now made a straight line. And this, in case you have not been told before, is an angle with a degree measure of 180 degrees. Straight lines measure 180 degrees. Okay, so here we go. I have two rays here that have the same endpoint. We'll call this endpoint Q, and then this ray was PQ, and this ray was QS or QR. So together they make one line, PQR, but that angle measurement is 180 degrees, all right? That angle measure there is 180. A straight line is 180 degrees. While we're still talking about angles, we're going to talk about congruent angles. Those are angles with the same measure, okay? Two angles with the same measure are congruent angles. And so it makes them congruent. And then our example, we might have we'll call this angle A, okay? We'll just name this angle A, and it's, I don't know, 45 degrees, okay? And then over here, we have another angle, and we'll call this angle B, and it's also 45 degrees, okay? These are congruent to each other, and there's a few ways we could write this, but I'm going to say angle, and that M with the symbol means angle, okay? The measure of angle A is equal to the measure of angle B. So we can say that angle A is congruent to angle B. All right? Adjacent angles. That's when we have two angles that share a common side. They're right next to each other. Two angles that share a common side. Two angles that share a common side. So here we have, I'm just going to draw the whole picture first, then we can talk about it. Okay, this is, we'll call this one angle 1, and we'll call this one angle 2. 1 and 2 are adjacent to each other, okay? They are next to each other. And with everything that we've learned about angles, that means that we can talk about postulates. This gives us a new postulate. And it tells us if we have an angle, and we're going to call it angle ABD. And we have another angle, DBC. DBC. And if they are adjacent to each other, they're side by side, the biggest hint that they are side by side here is in their name. They both share D and B, right? B is a shared vertex, are adjacent to each other. Then angle ABD, so angle ABD plus angle DBC is equal to angle ABC. So what I mean by this is if I have two angles, we're calling this one ABD, okay? This is B, This is A. This is D. ABD. And then I also have angle DBC. Okay, I have these two angles right here, these smaller angles that you see here. ABD, if I was to add it to angle DBC, if I were to add angle 1 to angle 2, it would give me the whole angle, ABC, the whole angle. Okay, and again, I write that angle ABD plus angle DBC equals angle ABC. All right. Angle bisectors. We've talked about bisectors. If I bisect something, I'm cutting it in the middle, splitting it in half. So an angle bisector is a line or ray that divides an angle into two equal parts. It is splitting it in half. A line or ray that divides, splits, an angle into two equal parts. Okay. So, for example, if I have, here is my angle, all right, and in my angle, we have a line or a ray that extends through the center. Has to be through the center. That is a bisector. And what it is doing, it is cutting the angle in half, okay? That's why both of these angles are congruent. And we know they're congruent because I have marked them with one tick mark each. So they are congruent to each other. The one tick mark is how I denote or how I say that they are congruent to each other. This is an angle bisector. Okay, we are almost done. Vertical angles. This is when we have two angles that are directly across from each other. Okay, two angles directly across from each other. So we have two angles directly across from each other on intersecting lines. Directly across from each other on intersecting lines. Okay. The thing about vertical angles is they are always congruent. Okay? Always congruent. They're the same. Okay, so just make a little note there. So for example, if I have two lines that are intersecting each other, here are my two lines intersecting each other. And it forms a few different angles here, right? We have four different angles here. So this is angle 1, this is angle 2, this is angle 3, this is angle 4. Okay? I know that vertically, 1 and 3 are across from each other. 2 and 4 are across from each other. So angle 1 is congruent to angle 3. And I can say the same thing about 2 and 4. Okay? If I have enough room, I'm going to try to write it right here. Angle 2, angle measure 2, is congruent to angle measure 4. Alright? They're right across from each other. So that makes them congruent to each other. They're the same. We are so close to the finish line, my guys. I hope that you had some popcorn and enjoyed the show. The last few things we're talking about is how we look at angles and how they work together. complementary angles. They complement each other. They build on each other. They are two angles with measures that sum to 90. Sum to 90 means that they add up to 90. Two angles with measures that sum to 90. Or that sum is 90, okay? So, there we are, 90 degrees. However, something to note, they do not have to be adjacent, okay? They don't have to be side by side. They just have to add together to make 90. That's important because some angles add up to 90, but because they're not adjacent, they're not right angles. Okay? If they're not side by side, they don't make a right angle. They just make a 90-degree angle. Do not have to be adjacent, all right? So first off, let's look at this is an example of adjacent complementary angles, all right? Let's say, and I'm going to go ahead and mark it with a square because they are making a right angle here. Let's just say 60, 30. They add up to 90, okay? But I could also have the example of a 60-degree angle. This one is 60. And then over here in a different area, this one is 30, all right? So these two are complementary. They add up together, right, and equal 90. These two are also complementary and add up to 90. However, these are adjacent, so they are also a right angle. These are not adjacent, so they are complementary, but they are not a right angle, right? Right angles have to form a 90-degree angle together and be adjacent to each other. Supplementary angles, like complementary angles, they are two angles with measures that sum, but they sum up to 180, okay? Two angles with measures that sum to 180. So just get that in really quick. Okay, and these also do not have to be adjacent. Do not have to be adjacent. Don't have to be adjacent. All right. So in this case, I will just give, I have this angle here. We'll say it's 120. And then I have another angle somewhere else that is 60. If you can imagine, I pick up this 60-degree angle and I were to move it and connect the two of them, it would be 180 degrees and we would have a straight line, right? And if that happens, we call those two angles a linear pair. A linear pair is adjacent angles that are supplementary. So they add up to 180. And if you were to combine them, they make a straight line. Okay. Combined, they make a straight line. Combined, they form or make a straight line. Almost there. All right, and this will be our last example for today. They combine to form a straight line. So let's do this one, and let's say that's 110. Okay, this one's 110. And then right next to it is an adjacent angle, because adjacent means they're side by side. But this one is 70. If I add them together, they're supplementary. They equal 180. Okay, but more importantly, if I am combining them, they are now a straight line. Okay, so linear pairs add up to 180. They are supplementary, and they are adjacent. They're side by side. So if you combine them, they make a straight line. This has been a deep dive into a lot of vocab, but we are going to be using this throughout the rest of the school year. We will be using these terms a lot. That's why it's important that we have this vocab now to refer to, we have it to study, and we have it just overall with those illustrations to kind of give us an idea of what we're looking for. I hope that this helped. If you have any questions, please don't hesitate to see me. Have a great day.